Now we'll discuss spring mass model. So we have the spring which is attached to a mass, say m. Now in this state, the system is in static equilibrium where gravity is balanced by extension in the string. Now at this state, suppose we displace this mass by a vertical displacement y, then the spring force minus ky, it will act on the system, and this force, it is represented by my double dash, or we can write this as my double dash plus ky equals 0, which is homogeneous linear differential equation in order 2 with constant coefficients. Now if we write its characteristic equation, it will be m lambda square plus k equals 0, or lambda equals plus minus under root k by m. Now suppose this under root k by m is plus or minus omega naught. From here we can write its general solution y as a function of t as a cos omega naught t plus b sin omega naught t, where omega naught is under root of k by m. This is the case of undamped oscillations, and this motion is called as harmonic oscillations. Now if we want, we can also write this as under root of a square plus b square, and we write this as a upon under root of a square plus b square cos omega naught t plus b upon under root of a square plus b square sin omega naught t. Now if we take this as sum cos delta and this as sum sin delta, we can write this general solution as yt equals a naught cos omega naught t minus delta, where a naught is under root of a square plus b square, and tan delta, it is equal to b by a, which basically is a shifted cosine curve. Now what we'll do is we'll add damping in the system. And here what we'll assume is, we'll assume that this damping force, it is proportional to velocity of the system, y dash. And because velocities are generally very small, it is a very good approximation. So in this case, we'll say this damping force, it is given by minus c y dash. Now with this damping force, this mechanical system can be expressed by this second order differential equation as m by double dash, and it is equal to minus this spring force and this damping force. So we can write this as m by double dash plus c y dash plus ky equals 0. Now we'll write its corresponding characteristic equation. So it will be m lambda square plus c lambda plus k equals 0. So from here we can write this lambda is minus c plus minus under root of c square minus 4km upon 2m, which is minus c upon 2m plus minus 1 upon 2m under root of c square minus 4km. Now here we'll use a short notation. We'll let alpha as c by 2m and beta as 1 upon 2m under root of c square minus 4km. So now we can write this lambda 1 as minus alpha plus beta and lambda 2 as minus alpha minus beta. Now again, depending on this value of c square minus 4 km, we'll have three separate cases. Case 1, when c square minus 4 km, it is greater than 0. In this case, we'll have two distinct roots, lambda 1 and lambda 2, and this is the case of overdamping. And then the second case where c square minus 4 km equals 0. Here we'll have a double root. And this is the case of critical damping. And finally, we have this third case when c square minus 4 km, it is less than 0. And in this case, the roots are complex conjugates. And this is the case of underdamping. So depending on the discriminant of this equation, we'll have three cases of overdamping, critical damping, and underdamping. Now we'll discuss this first case of overdamping. So in this case 1, where we have c square minus 4 km is greater than 0, we'll have overdamping. And in case of overdamping, we'll have this solution as yt equals c1 e to the power lambda 1 t plus c2 e to the power lambda 2 t, where lambda 1 is minus alpha plus beta and lambda 2 is minus alpha minus beta. So it'll be this c1 e to the power minus and then alpha minus beta t and plus c2 e to the power minus alpha plus beta t. Now typical motion in overdamped case, it is represented by these three lines 1, 2 and 3. And in all these cases we have taken positive initial displacement, and in the first case we have taken positive velocity, in the second case we have taken zero velocity, and in the third case we have taken negative velocity. So this is the general motion in the overdamped case. Now we'll take on this second case of critical damping. Now in this second case, when c square equals 4 mk, where we have condition of critical damping, in this case both lambda 1 and lambda 2, they are equal to minus alpha and value of beta is 0. So for this case, its displacement is represented by c1 plus c2t into e to the power minus alpha t. So displacement in the case of critical damping, it is given by this equation. Now for different values of c1 and c2, if we consider its typical graph, if we take positive initial velocity, then its motion will look like this first dotted line. If we take v as 0, it will be the second dotted line, and if we take v negative, then the motion will be along either of these two lines depending on values of c1 and c2. Now essentially this first case of overdamping, it is non-oscillatory motion, and this third case of underdamping is oscillations. So basically this case, c square is equal to 4 mk, it marks the border between non-oscillatory motion in overdamping and oscillatory motion in underdamping, and that's why we call this as a critical case. Now we'll come to its third case, which is case of underdamping. Now in this third case of underdamping, the condition we have is c square minus 4 mk, it is less than 0. And if c square minus 4 mk is less than 0, what we'll do is we'll know that this beta, which is under root of c square minus for mk will be purely imaginary. So we'll assume that it is equal to some iota into omega star. So for this case, we'll have two values of lambda. It will be minus alpha plus iota omega star and lambda 2, which is minus alpha minus iota omega star. Now we can write its general solution as yt equals e to the power minus alpha t into a cos omega star t plus b sine omega star t, and we can also write this as e to the power minus alpha t, and it will be a naught cos omega star t minus delta, which we have discussed in the previous example. Now this case, it will represent damped oscillations. This part, a naught into e to the power minus alpha t, will form an envelope. And this cosine part will make an oscillatory motion. So in this case, we'll have these damped oscillations. So essentially, this third case is still an oscillatory motion where this amplitude is decreasing according to this envelope a naught e to the power minus alpha t. So these are the three cases possible in case of damped oscillations: overdamping, critical damping, and underdamping. Now there is one more condition possible in oscillations, and that is forced oscillations. In forced oscillations, we'll have my double dash plus cy dash as damping input and plus ky as spring force, and it will be equal to this RT, where RT is called as input or driving force. Now with this RT, there are many cases possible, but of all the cases, the situation is interesting when this input force is a periodic function. So what we'll do is, in our case, we'll assume this driving force as some cosine function. So let it be f naught cos omega t. So now we can write this differential equation as my double dash plus cy dash plus ky, and it will be equal to f naught cos omega t. Now general solution for this equation, my double dash plus cy dash plus ky equals f naught cos omega t, is sum of general solution of my double dash plus cy dash plus ky equals 0, which we have already studied in the previous section. And let us say this solution is yh, and then there will be this particular solution when we have this deriving force, and let that solution be yp. We can find this yp by the method of undetermined coefficients, and we know that since it is sinusoidal function, this ypt, it should be of the form a cos omega t plus b sine omega t. Now if we differentiate this, we can write y dash as minus a omega sine omega t plus b omega cos omega t, and y double dash will be minus a omega square cos omega t and minus b omega square sine omega t. Now we substitute it in this equation. We can write m and minus a omega square cos omega t minus b omega square sin omega t plus c, and will be minus a omega sin omega t plus b omega cos omega t plus ky will be a cos omega t plus b sin omega t, and it will be equal to f naught cos omega t. Now what we'll do is we'll take cos omega t together and sin omega t together. So we'll write this as this a into k minus m omega square. So it will be this a into k minus m omega square plus bc omega into cos omega t, and the same way we can write it for sin. So it will be this b into k minus m omega square minus ac omega sin omega t, and it will be equal to f naught cos omega t. Now if we compare cos and sin, then we get two equations which are a into k minus m omega square plus bc omega. It will be equal to f naught and b into k minus m omega square minus ac omega will be equal to 0. Now from here we have to find the value of a and b. So basically these are two linear equations. From the second one we can write b as ac omega upon k minus m omega square, and we'll put it in this first equation. Then it will be a, we'll take common, and it is k minus m omega square plus c square omega square upon k minus m omega square, and it will be equal to f naught. So basically this a, it will be f naught into k minus m omega square upon k minus m omega square whole square plus c square omega square, and if we put a here, we'll get this b as, now in this case k minus m omega square will cancel, so we'll get f naught c omega upon k minus m omega square whole square plus c square omega square. If we take under root k by m as omega naught, which is natural frequency of the system, then we can replace this k with m omega naught square. So now we can write it as a equals f naught m into omega naught square minus omega square upon m square omega naught square minus omega square whole square plus c square omega square, and value of b will be f naught c omega upon m square omega naught square minus omega square whole square plus c square omega square. Now once we have the value of a and b, we can write general solution yt as yht plus ypt, where yht is general solution of homogeneous equation and ypt is particular solution of this forced oscillations. And for further analysis, if you want, you can work out condition of resonance in undamped force oscillations, where we'll take C as 0, and we can find damped force oscillation when C is greater than 0. And this is how we study oscillations using second order differential equations.